Welcome everyone. We'll talk in this piece of the lecture on issues related to parameter estimation. So first I'm going to talk about the case when we have time varying parameters to be estimated. Then we'll see the connection between Kalman filter and the recursive least square estimators. Then we'll talk about the persistent excitation conditions. And finally, we'll talk about parameter estimation when we work in closed loop control systems. So I'm assuming the usual model where we have y as an output, which is measured, and I as the sampling index, and theta, the unknown parameters. But here we'll assume that theta is time varying. So the system is linear in the parameters, but we assume that theta could vary, and E is the independent sequence of noise that have zero mean and constant variance. We'll have two possibilities for the variation of the parameter theta. One possibility is to have abrupt changes, like sudden changes in the values of the parameter. In that case, actually, what we do normally in parameter estimation is to reset the covariance matrix P of t to a value equal some constant r times the identity with dimension n by n, where n is a dimension or the number of parameters to be estimated, and r is some big number to reflect that something big has happened concerning the change of the parameters. And we continue our recursive least square using the value of P of t as we do it. This is one case. The other case is when the parameters vary slowly. In that case, we modify the index that we are minimizing to calculate the value of the estimated parameter. We have added here a factor lambda. We call lambda forgetting factor. We'll see why it's called forgetting factor. Typically, the value of lambda is greater than 0 and less than or equal to 1. Actually, it shouldn't be equal to 0. It is greater than 0 but less than 1. And typically, it would be something like 0.9 up to, say, 0.99 in most applications. Now, let's see the effect of lambda on the parameter estimation. Suppose that we have measurements that vary from 1 to t, where t is a big number, like the number of measurements is big. So if we take the index I around 1, that means the difference between t and I would be almost equal to t, and t is a big number. So that means that lambda, which is a number between 0 and 1 to the power t, would be something that will go almost to 0. What does that mean? It means that the old measurements, which are around 1, so the early measurements, will be weighted by a very small number. So we are almost trying to forget the effect of these previous measurements on our performance index, and consequently the new estimates will not rely much on that history. However, if we take I close to t, that means t minus I will be around 0, and that means lambda to the power 0 will be equal to 1, which means that we give full attention, we get 100% weight to the measurements that are recent in our measurements. So this is why it's called forgetting factor, because that factor actually gives less weight to earlier measurements and higher weight to recent measurements, and that would help us to base our estimates, the new estimates of theta, based on the new measurements, so we'll be able to catch the variation of the parameters as we have explained. In that case, the equations for the recursive least square will be just modified a little. The first equation of estimating theta hasn't changed at all. However, here in calculating the gain k, we notice that lambda has appeared here in the denominator. Also, in calculating the covariance matrix P, we are dividing here by the forgetting factor. So that's how we can readjust the recursive least square estimator to take into account the case of slowly changing parameters. We can relate actually the recursive least squares to Kalman filter. If we assume a process with a state space representation like this, where theta here would be the state variables and y is the output measurement, then we can design an optimal observer. The optimal observer will take the form theta t plus 1. In that case, theta hat would be the observed states equal theta of t plus a gain, and that gain has to be the optimal gain according to Kalman design, and that would be multiplied by the difference between the output measurement and the calculated measurement. In that case, it would be phi transpose times the states of the observer. So if we carry out this setup, actually what we get would be again the equations of the recursive least squares. Gain k would be just calculated as we have seen in the recursive equations, and in that case the recursion starts with assuming some initial distribution with mean theta of 0 and a covariance matrix P of 0. So the covariance matrix, the initial covariance matrix would be corresponding to the covariance of the initial estimate of the states. Now we'll move to an important topic, and this is the persistent excitation condition. Remember, when we derived the least square estimate, we said that the matrix phi transpose phi inverse must exist, and this is actually a condition that, as we will see here, related to the persistent excitation condition. So let's start as an introduction by considering a single input, single output y over u with corresponding transfer function g of z. Now we know that by definition g of z would be a summation from k equal 0 to infinity to g of k times z to the minus k. If we assume that this transfer function is stable, it means that the impulse response coefficient g of k will actually decay to 0. And if that happens, we can truncate the summation instead of a summation to infinity to some number n. In that case, if we give the values of the impulse response the symbol theta, then we can rewrite the summation as theta 1 z to the minus 1, theta 2 z to the minus 2, and so on up till theta n z to the minus n, where theta 1 in our definition would be, say, g of 1, and theta n would be that g of n. And we assume that these coefficients are not known. If we do that, we can write the difference equation, the corresponding difference equation of the system, as y of k equals theta 1 uk minus 1 up to theta n uk minus n. Actually, this model is called moving average model. And we can write the expression of y as phi transpose k times theta as usual. So we ended up with a moving average model, and we will depend on that to study the conditions that will make phi transpose phi invertible. Actually, the reason I said that is that because in most of the cases when people talk about persistent excitation, they thus consider the phi matrix as composed of the inputs. So I indicated here why this is true, and this is enough in order to study the question of excitation. Okay, so if we do that, we can calculate the product phi transpose phi as we agreed before, the columns phi of k times the row vectors phi transpose. And in that case, the vector phi would be composed of the values of u from k minus 1 up to k minus n, where n is the number of the parameters to be estimated, and the row vector would be just the transpose of that. Now, if we multiply these two vectors together, we will get an n by n matrix, and the diagonal elements of this matrix would be just the square of the values of u at the different instance, while here we'll have uk minus 1 times uk minus 2, and then the shift will increase till we reach here uk minus 1 times uk minus n. And this matrix actually is symmetric, which means that this part of the matrix, the upper diagonal, is similar to the lower diagonal part. Now we will define a matrix here. We call it the empirical covariance matrix, and that matrix is the limit as t goes to infinity when we have a very large number of measurements of 1 over t multiplying phi transpose phi. In that case, each element of the resulting matrix C of n, the empirical covariance matrix, will be a limit as t equal to infinity of 1 over t times the summation of ui times ui minus k. So if we take, for example, k equals 0, that will give me C of 0, and that would be the limit as t goes to infinity of 1 over t, the summation as I goes from 1 to t of u of I squared. So this is like the diagonal elements of the matrix capital Cn that we talked about. If we take, say, k equals 1, we get C of 1, and that would be the limit as t goes to infinity 1 over t, the summation of u of I times u I minus 1. This is I move from 1 to t, and this is like the correlation between points on the signal that are shifted one sample, and so on. So the matrix, the capital matrix Cn, could be then written as C of 0, C of 1, up till C of n minus 1. And here on the diagonal we'll have always C of 0, and the off diagonal will have here C of 1, and so on. And as I said, this part of the matrix is symmetric, so these two upper and lower diagonal components of C will be the same. Now the condition for the signal, the input signal, to be persistent exciting is that the rank of Cn should be equal to n, where n is the number of estimated parameters. So you can see now the connection between this covariance mix and the persistent excitation condition. However, let us talk from a physical point of view about the meaning of persistent excitation. Suppose that you have a plant, say a motor, with constant input, and assume the system is stable, so the output at steady state will be constant as well. As we can see here, there is no variation in U, no variation on Y. Then if I collect input and output measurements and put that to the recursive least square estimator, I will get actually nothing, because the dynamics of the system are not shown here. Now, how would I go around that? I should actually make some changes in the input. So if the input changes, then I would expect the output to change correspondingly. So for example, I could get something like this. Now these transients reflect the dynamics of the system. So if I collect now the input and the output measurements, and I use least squares to estimate the parameters of the system, I would get for sure better results than or more accurate results than what I would get from using just constant input at the input of the plant. And now the persistent excitation condition is trying to investigate how would U should look like in order for the output to exhibit all the dynamics that we would like to show in the system, and consequently to estimate the corresponding parameters that can be used later on for control design. Okay, let's now see the persistent excitation characteristic of some of the common signals. The first signal that I'm considering here is the delta function, and we know that the delta function, if we plot it, it will have value 1 at 0, and it is 0 otherwise. So if we calculate the coefficient C node, it would be the limit as t goes to infinity of 1 over t, the summation of delta k minus 1 squared, where k goes from 1 up to t. And since the delta function is only 1 at k minus 1 equal to 0, which is k equal to 1, then the whole summation here would be just equal to 1. And then the limit will be the limit as t goes to infinity of 1 over t, and that will be 0. And conclusion, that the delta function, the persistent excitation of the delta function, the degree of that is equal to 0, which means that we cannot really use the delta function as an input signal to carry out parameter estimation experiment. Let's move then to the unit step function. The unit step function would be 1 for all positive values of k, and 0 otherwise. This is the unit step function. So if I apply the same definition, I would calculate C of 0 as the limit as t goes to infinity 1 over t, the summation from 1 to t of the unit step. The unit step is 1, as we mentioned, and it would be 1 squared. So 1 squared is just 1, and summation from 1 to t, that will give me t, and t will cancel out with 1 over t. So the net result would be just C node equal to 1. I can calculate also C1, and that would be the limit as t goes to infinity of 1 over t of the summation uk minus 1 times uk minus 2, and this is from 1 to t. And similarly, since u and k minus 1, u, k minus 2 will be only ones, then the summation will give me, from 1 to t will give me t, and t will cancel out with 1 over t, so the result will be 1 again. But what does that mean? It means that if I write the empirical covariance matrix in case of taking two elements, it will be consist of two dependent columns, because the two columns here are similar. So I cannot claim that C2 is a valid empirical covariance matrix. The only choice I will be left with is to take n equal to 0, and that means that the unit step function is persistently exciting of degree 1. So the degree of persistence of excitation for the unit step is just 1, since I only would have a matrix of dimension 1 by 1 to represent the empirical covariance matrix. And that also means that you can use the step function just to estimate one parameter. The second case I like to consider here is a sine function. So if I take again C node as the limit as t goes to infinity of 1 over t, the summation over k from 1 to t, the square of the function, so that would be sine omega k minus 1, and this all squared. I can write that as a limit as t goes to infinity of 1 over t, the summation of, I will just use the trigonometric equivalence of sine squared, so it will be 1/2 minus 1/2 cosine, double the angle, so it is 2 omega k minus 1, and here from 1 to t. We know that for the cosine twice the angle, if you take the summation over a large number of points, then that summation, since the cosine function is symmetric around the time axis, the summation will be equal to 0. That means I will end up taking only summation of 1/2 from 1 to t, and that will give me 1/2 times t, but t will cancel out with the 1 over t, so the result of this would be just 1/2. So this is the value of the coefficient C0. I can also calculate the coefficient C1, and that would be the limit as t goes to infinity of 1 over t, the summation from 1 up to t of sine omega minus 1, sorry, it's omega times k minus 1. This is multiplied by sine omega k minus 2. And again, I'm going to use the trigonometric relation of the multiplication of two sine functions. So that will give me the limit as t goes to infinity of 1 over t, the summation of cosine omega minus cosine 2 omega k minus 3 omega, and that is divided by 2. And here the summation from k equal 1 up to t. Once again, the summation of cosine this angle will be equal to 0, and the cosine omega is not dependent, this term is not dependent on k, so it will remain as a constant. So I will have cosine omega over 2 outside the summation, and summation from 1 to t, that will give me t, and t will cancel out with 1 over t. So the net result would be just 1/2 cosine omega. And now if I write the empirical covariance matrix C, it would consist of 1/2, this comes from C node here, and 1/2 cosine omega, here 1/2 cosine omega, and here 1/2. We call that C2. And as you can see, the two columns here are independent. So we conclude that the rank of C2 is equal to 2. So the degree of the persistent excitation of the sine function is equal to 2, and that means that we can use the sine function to compute two parameters. Actually, we can notice that if we take the Fourier transform of the sine function, this is the frequency axis, and this is the Fourier transform of the sine function. It would consist of two components at omega 1 and minus omega 1, where omega 1 is the frequency of the sine function. So it has two components, and those correspond to the two parameters of the degree of excitation. So another way to look at the degree of excitation of a certain signal is actually to do the Fourier transform and see the frequency components of that signal. Instead of calculating the empirical covariance matrix, there is actually an equivalent theorem that would enable us to check the persistent excitation degree of a given signal u. And according to the statement of that theorem, if we have a signal u, it would be persistently exciting of order n, if and only if the limit as t goes to infinity of 1 over t of the summation of a polynomial a of q times u times the signal that we are interested in, all that squared, is positive. And this has to be true for all non-zero polynomials a of the degree n minus 1 or less, where n, as we said, the persistent excitation degree. How we implement that theorem? Actually, we know the characteristic equation of the common signals. Like, for example, if we consider the unit step we know that the characteristic equation of the unit step is q minus 1 equals 0, because if we multiply q minus 1 by the unit step, that would give us 0. So the characteristic equation of the unit step is this. So this is a polynomial, it's a non-zero polynomial. If we multiply it by u, it will give me 0. Now if I take a polynomial less than that, it would be a polynomial of degree 0. So if I take a, according to the theorem, equal to some constant, any constant, say c1, then I guarantee that the summation of c1 times the unit step squared, where k goes from 1 up to t. I guarantee, since this the unit step is 1 and c is a positive constant, then the summation will be positive. So I will guarantee that this will give me a positive number, and consequently for any polynomial a of degree 0, I guarantee that the condition of this theorem is satisfied. So I would say then n minus 1 equals 0. 0 here is the degree of the polynomial A, and I conclude from that n equals 1, which means that the unit step is persistently exciting of degree 1. So that's how we apply the theorem. Another example, if you consider the sine function. The sine function, we know that the characteristic equation of the sine function would be of second degree. And consequently, if we take a polynomial of first degree, then we will guarantee that the condition of the theorem is satisfied. So n minus 1 would be equal to 1, and that will lead to n equal to 2. And consequently, we conclude that the sine function has a persistent excitation degree equal to 2, and so on. Now, is there a function that actually guarantees correct excitation for any order? The answer is yes, and this would be the white noise. So the white noise is persistently exciting of any degree. This is the best signal ever you can use as an input in order to do parameter estimation. However, we can simulate the white noise by what's called the pseudo binary random number. Binary random number. And this is a signal that changes value, like if this is k and this is the signal u, it changes value between two given numbers, say 1 and minus 1, doesn't have to be 1. However, the instant at which the signal changes from the two numbers, that's why it's called binary number, the instant at which this switching occurs is random. So you would get something like this. So this instance of change from 1 to minus 1, these occur at random instance of times. Actually, this is a good simulation in practice to simulate the white noise, and that signal is actually used instead of the white noise. If we are talking about deterministic systems, then actually a square wave function can do the job. And the reason that if you plot the square wave function, these edges of the function, if you do Fourier transform for the signal, you will find a lot of frequencies, we call that harmonics, generated because of these edges. And these harmonics, which are generated because of the edges, would actually provide a good source of excitation for deterministic systems in order to estimate their parameters. So commonly in deterministic systems, it is enough that we take a square wave as an input function to do the parameter estimation experiment. The next point that I'd like to discuss here is actually the effect of closed loop identification on parameter estimation. Actually, I'm not going to give any general theoretical results on that, but just a simple example to illustrate the difficulty that one may encounter when dealing with system identification in closed loop. So I'm considering here a first order system where u is the input and y is the output, and they are both measured, and a and b are the unknown parameters to be estimated. Now I'm assuming that this system operates in a feedback loop where the control signal u of k is just a gain times the output. Now if you assume that we multiply the control signal by any constant, arbitrary constant alpha, then I would get alpha u time equals minus alpha gamma y. And if I add these two equations together, say this is equation number 2 and this equation number 1. If I add equation 1 and 2 together, I will get a new equation, say number 3. And in the new equation, here should be y of k. In this new equation, the parameters of the equation would be a minus alpha gamma and b plus alpha times u. So these are the parameters to be estimated by taking the measurements y and u. So a hat would be a minus alpha gamma, and b hat would be b plus alpha. And if we eliminate alpha from both equations, I get this relation between b hat, the estimated parameter b hat, and a hat. And as we can see, it is a relation of a straight line. The true values that I should get from the parameter estimation experiment would be just a point on this straight line. Now, the difficulty in this problem or this setup is that actually the index function, the cost function that we are using in order to estimate the value a and b, will have the same value on every point on the straight line. So that means that there is no guarantee that the parameter estimation experiment will converge to the true values. It could converge on any point on the line and still give the same minimization index that we are looking for. So the reason for this phenomena is that we are using this simple feedback law for our setup. So what is the problem? One of the solutions is actually, instead of having a direct feedback from y of k, I would introduce a delay here. So I would use u of k equals minus some constant gamma times yk minus 1. That will break the difficulty. This is one alternative. A second alternative is to use more complex control law, like you would have two terms, constant times y of k and another constant times yk minus 1. This is will also solve the problem. A third solution would happen if we have an external signal applied, a reference point or a set point applied to the system. So there are solutions to the problem, but the main message in the problem is that in feedback you could have some problems associated with the convergence of the parameters to their true values, and that requires us to look carefully about the problem when we have a closed loop identification experiment to be carried on. So this actually finishes what I wanted to say in this piece of the lecture, and I'll see you in the next piece. Thanks.